Let's take a look at section 1.3, which continues our study of the nature of problem solving. In this section, we are going to look at exponential notation. So when we multiply the same numbers, we can use exponential notation to simplify that task. And so here you can see three different examples of that. So you have 10 times 10 times 10, and we can simplify that as 10 to the third power. Sometimes you'll hear this referred as 10 cubed. If you multiply 6 times itself 8 times, then that can be reduced down to 6 to the 8th power. Similarly, if you multiply 15 times itself, I believe that's 9 times, then that can be reduced to 15 to the 9th power. So that's just exponential notation helps us to, rather than having to write all of these things out so many different times, then you can just, it shortens it down and makes it a lot easier to write things in exponential notation. Now with exponential notation, we're going to have some identity rules, and in order to go over those identity rules, we need to kind of go over some basic definitions first. So some basic exponential notation definitions for any non-zero number b, which is considered our base in any counting number n. So if you'll take a look right here, and this b right here is called our base number. N is our exponent, and that n represents the number of factors of b, which is our base, and b cubed. So b is our base, and that tells us that we're going to have 3 of our bases, so 3 factors of b. Similarly, if you had 5 as your base to the third power, then you would have 5 times 5 times 5, which can be simplified to 125. Okay, so now let's look at a few identity rules. The most basic identity rule is that anything to the 0 power is equal to 1. Now, when I say anything to the 0 power, I mean anything to the 0 power is equal to 1. So any base to the 0 power is equal to 1. So x to the 0 power is equal to 1. 500 to the 0 power is equal to 1. X, y, z to the 0 power is equal to 1. If I said 5,262,000 to the 0 power, it's equal to 1. So anything to the 0 power is equal to 1. I could show you the mathematical proof of that. If you're interested in that, you just let me know. It's rather long and ugly. You could just take my word for it, but it is a rather long proof. But if you're interested in it, you just send me a little email and I can gather that up for you. Or you could just take my word. The next identity rule has to deal with negative exponents. And so here you can kind of see this rule. And if you can imagine that everything is understood to be over 1. So if if this is understood to have an imaginary, imagine this is a fraction over 1. And what we can do is take the reciprocal of this, and when you take the reciprocal of it, it becomes a positive exponent. So taking the reciprocal of this becomes what you see right here, 1 over b to the n. And so that's sometimes hard for students to remember. So what I like to say is that you strive to have no negative exponents, and to fix it, rather than saying take the reciprocal, I usually just say to fix it, flip it and change the sign. So that's my South Alabama terminology. Tends to kind of stick a little bit better. But flip it and change the sign, not necessarily as formal mathematics, but anyway, that tends to work. So x to the negative 2 power, in order to make this positive, imagine that this is all over 1. So if you would flip that and change the sign, then you would turn that into 1 over x to the positive 2. And so that we flipped it and then we changed it to a positive 2. Okay, so k to the negative 5th. Again, imagine this is over 1. Then we're going to flip that, and it's going to become 1 over k to the 5th. Okay, then 1 over a to the negative 9th. Flip that. So when you flip this, you have a to the negative 9th is in the denominator. So you're going to flip it, so that actually brings it to the numerator. So that would become a to the positive 9th. Okay, all over 1. So now you can kind of see it also works whenever you move it from the denominator to the numerator. So it doesn't matter if it's in the denominator. If it's negative in the denominator, move it to the numerator. If it's negative in the numerator, move it to the denominator. So it works either way. So again, we're in the denominator and we're negative, so we need to move it to the numerator and make it positive. So that would be t to the 12th. And then lastly, if you have negative in both places, you actually can just swap places, okay? So we're going to move this term up here. We're going to move it to the denominator. Then we're going to move the bottom term, move it up to the numerator. So we're just going to flip this whole thing upside down. So whenever you do that, you have y to the 5th over x to the 3rd, and everything becomes positive then. Okay, so that's how you can make negative exponents positive. All right, so that is our negative exponent identity rule. All right, next topic in section 1.3 is the idea of fixed point notation, scientific notation, and floating notation. So the first one is fixed point notation, and that is what you typically see all of your numbers written in. So what you see here on the screen, 12.98, that's fixed point notation. That's nothing different than how you typically see numbers written. The second one is scientific notation, and it has a rule that says that your base number must be greater than 1 and less than 10. So when we look at 12.98, it fits the first part of this rule that this number is greater than 1, but it is not less than 10. So in order to fit this, scientific notation rules says that you have to move your decimal place. So what we're going to do is we're going to move our decimal place one time, or as many times until you fit this rule. So in this case, I only need to move it one time, because when I move it one time, I get 1.298. Now 1.298 is greater than 1, and it is also less than 10. Now I moved my decimal place one time, so for scientific notation, I have to tag on times 10 to the 1st. The exponent of this 10 is however many times you moved the decimal place. So I moved my decimal place one time, therefore the exponent of the 10 is a 1. Okay? Now the last thing that you need to know is how do you actually input this in WebAssign. So in WebAssign, you're going to have your answer is going to look like this. The answer box looks like this. So what they're going to want you to do is they're going to want you to type into these boxes. So you would type in 1.298 into that first box, and then times 10, and in that second box, you're going to type in a 1. So that's how you would type in your answer. So that's exactly how you type your answer in, and that's like the other half of the battle of doing your homework. So a lot of people get tripped up on that of how you actually put your answer in. So that's how you would do your answer. So, all right, now we have one more notation to go over. The final notation is called floating point notation. And floating point notation is very similar to I call it calculator notation, because typically the only time you see this is on a calculator. Typically it's written kind of funny. And when you see it in WebAssign, it often is kind of tricky. So you'll see it in WebAssign a lot of different ways. So you'll see it'll look something like this, or it may have 1.298 and it'll have a plus 0.01, or it might just say plus 1, or it might say a minus 0.1 or a minus 1. And that's why it's so tricky, because you would think that they're saying, oh, they want me to say 1.298 minus 1, which is, and then you just try to subtract 1. And so, but that's not what they're saying. And so this is the same exact number that we just talked about, 1.298 times 10 to the first power. It's just written in a different notation. So how this is actually going to be written in another way that you'll see it written in WebAssign is going to be in this multiple choice format. And so this is where it gets really confusing, because you'll see all of these different choices and they just look funny. And so you have to pick the right one. But you see this one right here, it looks funny, but anyway, you have to pick the right one. And so the correct one in this case is the third one there. And so just know that floating point notation is more like a calculator notation. Some scientific calculators, instead of like on a scientific calculator, you might, like my scientific calculator actually does it has like an E right here. It'll say 1.298 E01, and that's their floating point notation for scientific notation. So, so there's just a lot of different ways that you might see this written out, like on a calculator. All right, that's the final one for different types of notation. Let's look at some examples of some problems that you'll deal with these different types of notations. So this first example is putting this particular problem into the different types of notation. So in fixed point notation, you have 0.0006578. And so we want to put this into scientific notation. So in scientific notation, we need to change this base number into a number. We have to move the decimal place to a number between 1 and 10. So because it has to be greater than 1 and less than 10, let's move the decimal place 1, 2, 3, 4 times. When we move the decimal place 4 times, that's going to give us 6.578. And so because we moved it 4 times, now notice that when I moved my decimal place, when it started out, this was a very small number, okay? When you have a very small number, you're going to have a negative exponent. So you should always have a negative exponent when you have a teeny, very small number, okay? Or if you move your decimal place to the right, then you are going to have a negative exponent. So in the previous example, we had a larger number and we moved the decimal place to the left, and then we had a positive exponent. So I always think about bigger numbers require positive exponents, small numbers require negative exponents. So that just helps me to keep that in mind. Okay, so 6.578 times 10 to the negative fourth. So in WebAssign, that's going to help me to know that I'm going to put that in 6.578 times 10. And in that box, I'm going to put in a negative 4. Then let's look at how to put that in floating notation. Let's see what that's going to look like. In floating point notation, you have 6.578, and then you have this minus 0.4. So again, this always seems like it's a little weird because it looks like you want to just subtract 4. But again, that's calculator notation, okay? So a lot of times in WebAssign, this will come out as a multiple choice question. So you just want to match it up with the correct one. And so you have to be really careful because, like, notice these last two are very, very similar. They just have some numbers transposed here. So just be really careful whenever you're picking those choices. We're going to look at several examples where we're going to kind of go backwards now. We're going to go back from various formats back to fixed point notation. So let's take a look at, we are 4 to the negative 2, and I want to go to fixed point notation. So 4 to the negative 2, fixed point notation. So you have some different options on how to do this. One of the things that I want you to get in a habit of doing is using a calculator. Now, your choice of calculator, if you have a calculator that you feel very comfortable using, you just have to be careful whenever you're using negatives and exponents and fractions and all of that. I suggest using a good scientific calculator. For the purposes of this video, just so that everybody can kind of get a calculator that everybody can access, Google actually has a free scientific calculator. So I'm going to pull that one up. So if you just Google and you just Google free scientific calculator, this is what you get. And it's actually pretty decent. So, so I kind of like it. So I'm going to show you how to do these examples on this calculator because everybody can access this calculator on any device. You are going to do 4 to the negative 2. So on this particular calculator, you will do 4, and then you're going to do your exponent. And then to do a negative, you just do the minus sign 2. So it's just like you see it. Now, in some calculators, and then you hit equals. On some calculators, you will actually hit, there's like a plus minus key, and so you'll actually hit that positive negative key. But in this particular calculator, you just hit the minus sign. So this gives you the answer 0.0625. All right, so on here we will go 0.0625, and that would be your answer. Okay. Then your next one is 4.78 times 10 to the negative 3. Now, is this going to be a big number or a small number? So again, you've got a negative exponent here, so you should expect this to be a small number. So what you can do is simply just move your decimal place 3 times. So we're going to move this to be a small number. So we want to move this to make this a small number. Are we going to move it to the right, or are we going to move this to the left? We're going to move this to the left. And so you would move this 1, to 3 times to the left. You would add in zeros anywhere that you need to fill in those holes. Okay, and then that becomes your new number. All right, so it's 0.00478. All right. Now, 7.98 and then the minus 6. This is a really good example of a floating point notation, which is that calculator notation. And most people will want to simply put this into their calculator and say this is going to be 7.98 minus 6, and they will get this wrong. Okay, because this is really 7.98 times 10 to the negative 6. Okay, that's 10 to the negative 6 power. It's a calculator notation. So again, is this going to be a big number or is this going to be a small number? This is going to be a very small number because that's going to be a negative exponent. So you're going to need to move this decimal to the left 6 times. So we're going to move that 6 times, and whenever you move that 6 times, that's going to make it a very, very small number. So you have 0.00000, maybe I said 5 zeros, not sure, 798. If I didn't say it, I meant to. All right, so remember that's a calculator notation and not a subtraction problem, okay? All right, last one. This is another type of floating point notation. And this, remember I told you a lot of calculators will use this E. And so is this going to be a small number or a big number? This is going to be a big number because you have a positive. So you're going to move this decimal point to the right 4 times. So we're going to move that to the right 4 times. So you're going to get the big number, 56,100. All right. Hopefully you understood all of those. Okay, now we have a couple of these on your homework assignment. I've taught this multiple different ways over the years, and I have found that this is the absolute easiest way to teach this, is basically to, this looks like a really ugly problem, but it turns out to be not nearly that bad. So what we're going to do is we're going to take this problem and we're going to simplify it. We're going to take this and we're going to get it out of scientific notation. Then we're going to use our calculator and we're going to work it out. And then we're going to put the answer back in scientific notation because that's the way they want it in WebAssign. Okay, so let's work through these steps. We're going to take each individual part. So we're going to take 4 times 10 to the 4th. So let's take this out of scientific notation and put it in fixed point. 4 times 10 to the 4th. It's actually pretty easy. 4 times 10 to the 4th is just 4 with 4 more zeros. Okay, so 4 with 4 zeros is 40,000. And then 6 times 10 to the 6th is 6 with 6 zeros. So that would be 6 million. Okay. And then 3 times 10 to the 5th is 3 with 5 zeros. So you have 300,000. All right. Now this is where you grab your calculator. So let's grab the calculator again. All right. So we're going to grab our calculator and we're going to say, all right, so I'm going to clear that out and we're going to say 4 with 4 zeros, 1, 2, 3, 4, times 6 with 6 zeros, 1, 2, 3, 4, 5, 6. And then I'm going to go ahead and hit enter because that's my numerator. And that's a really big number.
And I really probably should write that down, but since it's in my calculator, I'm not going to worry about that. Okay, so that's your numerator. That's the 40,000 times 6 million. Now I am going to hit divided by. So divided by the denominator, which is 3 with 5 zeros. 1, 2, 3, 4, 5. And then I'm going to hit enter. And you get this 8 with 5 zeros. Okay, you get 800,000. All right, that is your answer, is 800,000. All right, so in WebAssign, you're going to have this answer block, and it's going to look like this, because that's how they're going to want the answer. So now you just have to take 800,000 and put it into scientific format. So in scientific notation. So that's not hard at all. We just take, and our decimal place is here at the end. We're going to move it until we get all the way to the 8. So that's 1, 2, 3, 4, 5. So I moved it 5 times. So it's 8 times 10 to the 5th. So really, it looked like an ugly problem, but it really turned out to not be bad at all. It's a calculator problem. And I like those. They're not bad. Okay. So let's look at one more of these that's just slightly a little bit more difficult. All right. Threw in a negative exponent here. So just a little different. So let's take a look at this. All right, on this one, remember we're first going to take each individual one, put them into fixed point notation, and then use our calculator. All right, so 6 times 10 to the negative 6th. This is negative 6, that means it's a small number. So really, I'm going to make this a small number. So it's like 5 zeros and then a 6. Okay, so that's what we get here. So 1, 2, 3, 4, 5 zeros and then a 6. All right, and then you're going to have 8 with 8 zeros. Big number. 8 with 8 zeros. Okay, and then in your denominator, you're going to have 6 with 5 zeros. All right, then we're going to grab our calculator. All right, so let's clear this out. And we're going to do point, and we're going to do 5 zeros, 1, 2, 3, 4, 5, and a 6. And then times 8 with 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to hit enter. And then I'm going to hit divided by. And I'm going to do 6 with 5 zeros. 1, 2, 3, 4, 5. Enter. 0.008. Okay, 0.008. All right, so then remember we have WebAssign. In WebAssign, they're going to want your answer like this. So we have 0.008. So I'm going to have to move this decimal place 1, 2, 3. So I have 8 times, now what's going to go here? I moved the decimal place 1, 2, 3 times, right? But do I put a 3 here? What goes here? What do you think? This is a very small number. So hopefully you see that a negative 3 goes there. Okay, so 8 times 10 to the negative 3rd. Okay, Alrighty. Now, the last one is how many classrooms would be necessary to hold 1 million inflated balloons? Assume that one balloon is about 1 cubic foot and a typical classroom is 35 feet by 27 feet by 9 feet. Round your answer to the nearest number of classrooms. Okay, so we have to remember first the volume for a classroom is length times width times height. So we're looking at like a rectangular classroom. So if we're looking at the classroom that they gave us the dimensions of, we have 35 by 37 by 9. I think I changed in your notes. Okay, I did. So I apologize. Here in my slide, it says 27, but I ended up changing this to 37 in your notes. So just pretend that that says 37. All right. So then when you multiply that out, that's 11,655. 11,655. Let's double check and make sure I did that right. So 35 times 37 times 9. Yes, 11,655. Okay, then what you're going to do is you're going to take 1 million because you have 1 million inflated balloons and you're going to divide it by that total amount of volume. And when you do that, you get 85.8, something around that. Let's see what you get exactly. 1 million divided by 11,655. All right, so you get this long number here, but it's somewhere close to 85.8. All right, so this, though, says to round your answer to the nearest number of classrooms. So in other words, you can't have 85.8 classrooms, but 85 classrooms would not hold it because you still have to have at least 0.8 more. So you would need at least 86 classrooms. So that would be your answer, is 86 classrooms in this case. All right, you have a few word problems that are similar to this, where you're going to have to use some estimation and things like that. All right, that is section 1.3. If you have any questions, please feel free to reach out to me.
Okay, now we're going to look at the final two homework questions, which several people have a really hard time with, and I will say these are very tough questions. And so I want to look at number 16 before I look at number 15. So number 16 says, imagine that you've written down the numbers from 1 to 10,000. What is the total number of zeros you have recorded? And I know that some of your problems have a different number than 10,000, but 10,000 is the number that I wanted to look at in this example. So I'm going to walk you through that one, and then you can apply the same methods to whichever number you might have in your randomization of your problem. So let's take a look at this. The way we're going to do this is that we're going to divide this up into the different digits, okay? So I first want to look at the numbers that have just one digit in them, okay? So those numbers are the numbers 1 through 9, okay? If you look at numbers 1 through 9, there are no zeros in the numbers 1 through 9, okay? So no zeros in those set of numbers. Now let's look at the two-digit numbers. So the two-digit numbers, that would be the numbers 10 through 99. All right, now the numbers 10 through 99, so I put two blanks here on the screen. I want you to think about every number that could go in this first blank. So every number that could go into this first blank, there could be any set of numbers 1 through 9 in this blank, right? And so you could have 1 through 9 in that blank, but you couldn't have a 0 in that blank, right? But you could have a 0 in this second blank. So it turns out that there are only 9 different options and 9 numbers for that particular, to get in the 2-digit numbers, there are only going to be 9 different zeros. Okay, does that make sense? If you're counting the number of zeros, it would just be like 10, 20, 30, 40, 50, 60, 70, 80, and 90. All right, so there's 9 zeros. Now let's look at 3-digit numbers, and this is where it really starts to get a little crazy. All right, 3-digit numbers. Now everybody take a deep breath. Take a deep breath. Did everybody take a deep breath? Because this is going to be, you may need to go get like a Tylenol and a Coke or a coffee. Okay, so the first thing we're going to do is we're going to look at if you have 3 digits and only 1 0. Okay, so what I'm going to do is I'm going to put a 0 at the very last blank. All right. Now, I want you to think about possibilities of what would go in these first 2 blanks. We could have the numbers 1 through 9 here and the numbers 1 through 9 here. So there's 9 possible digits here, 9 possible digits here. Do you agree? Like, you know, does that make sense? Everybody shaking your head? Yes? Good. Okay. So it turns out that there are 9 numbers that could go here, 9 numbers that could go in that blank. And then, so I could multiply those together. So there are 81 numbers total that end in a 0 in this format. Can you give me one number like 110, 110, 120, 130, 140, right? Okay, that's one of the 81. Those are some of the 81 numbers. Okay. Now, it turns out we could put that 0 not just at the end of this blank. What about in the middle? I could put the 0 there, right? And I could put any digits 1 through 9 here and any digit 1 through 9 here, right? So there are going to be 81 different numbers that are in this format that have a 0 in the middle, like 101 and 102 and 202 and 203 and so on. There's 81 such numbers in that format with a 0 in the middle. Okay, with 3-digit numbers. Okay, are you with me? Now, that's with 1 0. Now, there's no more with just 1 0 because you're not going to have a 0 at the beginning of your number. All right? So that's it. We're just 1 0. So what I'm going to do is I'm going to come up here and I'm going to start like a summary of all of these numbers. All right. So for my 10, for my 3-digit numbers, with 10, I have two 81 numbers. Okay, so 81 times 2. Okay. Oh, I guess I'm not going to do that yet. Maybe not. 2 zeros. Okay. Sorry, I thought that was on this slide. Must be on the next slide. 2 zeros. All right. So for 2 zeros, I'm going to put 2 zeros right there. I want to know how many 2 zeros, if I have 2 zeros in a 3-digit number with 2 zeros at the end, how many possibilities are there? What are my numbers that can go here? The numbers 1 through 9, right? So that's 100, 200, 300, 400, 500, 600, 700, 800, 900. So there are a total of 9 numbers, and each one of those 9 numbers has 2 zeros, right? So that is 18 numbers. Okay? So for 3-digit numbers, I have 81 plus 81 plus 18, which gave me 180 zeros. Okay. All right, so that's a 3-digit number. Okay. Now, that gets me up to 3 digits. But I'm not quite there yet. Okay, so far I've gotten my 3-digit numbers, and I'm up to just my total for my 3-digit numbers. And now I'm up to my 4-digit numbers. Okay, so now for my 4-digit numbers, I need to look at, I'm going to do the same exact thing with 4 digits that I did with 3 digits, okay? So I'm going to start out with 10, and then I'm going to look at all the different possibilities. All right, so 10, I could have 9 digits in any of these other places. So I'm going to say there could be 9 in any of these other places, and there's 3 of them, right? So that's 729 numbers. 9 times 9 times 9. Okay, ending of 4-digit numbers that end in a 0. Okay, now I'm going to look at a 4-digit number that has a 0 in this 3rd place. Okay, and that's going to be a 9 digits here possible, 9 digits in the 2nd spot, 9 digits in this last spot. So that's also going to be 9 times 9 times 9. Okay, and then finally I'm going to have a 0 in this 2nd spot, and there are going to be 9 times 9 times 9 possibilities, 729 numbers there. So there are going to be 3 times 729 possibilities, which is 2,187 possibilities. Okay, so that is 4-digit numbers that have 1 0 in them. 2,187 possibilities. Okay, now I'm going to look at 4-digit numbers that have 2 zeros in them. So 2 zeros, I'm going to start out with 2 zeros at the end. 2 zeros at the end, then I can have 9 digits here, 9 digits here. So I'm going to have 9 digits times 2 zeros. That's going to be 81 times 2 zeros would be 162. Now I'm going to move my zeros to 2 different places, and I'm going to have them on the ends here. And I'll have the same thing, 9 times 9 times 2 zeros would be 162. And then I have one more combination with the 2 zeros in the middle. Okay, and so that's going to be the same thing with 162 of those numbers. All right, so that's 2 zeros. So I'm going to add that up here in the top. I'm going to add that, and that's going to be 3 times 162, so that's 486 possibilities with 2 zeros. Now let's look at 3 zeros, 4 digits with 3 zeros. Okay, so we're up to 4 digits and 3 zeros. Okay, so let's think about that. There's only our possibilities are getting better on this and fewer, because if you really think about it, there's only going to be the numbers like 1,000, 2,000, 3,000, all the way up to 9,000. So when you look at that, you're only going to have the 9 numbers. Those 9 numbers are going to have 3 zeros, so you're only going to have 27 zeros there. So when you add the 27 to that, and then you add all of those different numbers up, you get 2,700. So you have 2,700 zeros in with your 4-digit numbers. So now, this is as far as I'm going to take you on this particular homework problem. But remember that our question asked us how many zeros are there in 10,000. So 10,000 has 5 digits. Okay, 10,000 is a 5-digit number. So we went up to 4 digits, and so all you have to do is you would go up to the next. So you've gone up all the way to 9,999, and that's how far you've gone up here. And so 10,000, all you have to do is add the number 10,000 to this, just that one number. So you just count the number of zeros in the number 10,000, add that to it, and you should have the number. Okay, so really you're just a few little zeros away from the answer. Now, how would you work this out if you don't have 10,000? You would continue to go in the same pattern and until you get to your number. Okay, but you're working it out in the same exact pattern. All right, so that's going to be how you would answer this particular question. Okay, if that is clear as mud, then I would suggest replaying this video, this problem again. So hopefully this helped some. I hope it did. Okay, the last problem that I want to look at is homework number 15. And this one says if it takes 1 second to write down each digit, how long will it take to write down all the numbers from 1 to 1001? So this one is similar. We're going to work it similar to number 16. It's just a little bit different, but we're going to work it in similar fashion. Okay, so it's going to go a little bit faster though than the last one. All right, so we're going to start out with the single digits. So when we look at our one-digit numbers, that's going to be the numbers 1 through 9. And so if 1 second for each digit, that's just going to be 9 seconds total. Now, when we look at two-digit numbers, we're going to have some different options on this. So thinking about all of the numbers that can be in this first blank, that's going to be the number digits 1 through 9. So we have 9 choices, right? But now in the second blank, you actually have choices of 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0 that can be in the second blank. So you actually have 10 different digits that can go in this second blank. So that means that you would have a total of 9 times 10. This is a two-digit number, which according to the problem is going to take 2 seconds to write. And when you say 9 times 10 times 2, you're going to get 180 seconds. Okay, so two-digit numbers, you're going to get a total of 180 seconds for all of your two-digit numbers. Okay, so now let's look at three-digit numbers. For your three-digit numbers, you're going to do kind of the same process. Think about all of these different places. So in this first blank, you're going to have just the digits 1 through 9, right? So there's 9 options there. But then you're going to have also 0 can be included in both of these blanks. So you're going to have 10 different digits here and 10 different digits here. So you're going to have a total of 9 times 10 times 10, and because this is a three-digit number, it's going to take you 3 seconds to write it. So multiplying all of this out, it's going to take you 2,700 seconds. Okay, so three-digit numbers is going to take you 2,700 seconds. All right, and finally, let's think about four-digit numbers. So we're going up to 1001. So really, you only have the four-digit number 1000 and the four-digit number 1001. So when you look at that, that's really just 8 digits. So it's a total of 8 seconds. So I'm going to add 8 seconds. When you add all of those up, you would get 2,897 seconds. So that's the total for all of this. Okay, so that's going to be everything. Some of these problems on this one are like 998 seconds or something. I mean, like adding it up to 998. And so what I would do is I would probably calculate like up to a three-digit number, like up to that, which would get you up to 999. And then I would subtract enough to get down to I would subtract like the 3 digits that it would take to get to the 998 or whatever, or 6 to get down to 997. So just know that you can add or you can subtract to get down. So, all right. I hope that helps you with number 15, and that is going to conclude our 1.3 homework.